All right, ladies and gentlemen, so let's get started with electron configuration. So what we're going to talk about is the basics of quantum theory. And what quantum theory just means is the really, really small world we can't see. So like the world of electrons, the world of protons, all of that Ant-Man type stuff is what we're going to be discussing in this little unit. So we have some development when it comes to electron configurations and how we understand them. Most notable were the ideas of J.J. Thomson Rutherford and Schrodinger and Niels Bohr. The J.J. Thomson Rutherford model was more like it's called a pudding model, where all of the protons and electrons were smushed together in the middle of a nucleus, bound together real tight, and not exactly accessible or manageable. Well, through some experimentation and some better understanding, we were able to refine these ideas to more modern day examples. So what I have depicted here is like a combination between Bohr's model and Schrodinger's model. The more accurate definition is indeed Schrodinger's model, where they have electron clouds. That's that yellow you see around here where the density is real dark right here and it kind of fades out as you get to the outer edge, which signifies with a denser color means you have more likelihood of picking up an electron, simply because these little electrons, my little orange dots here, are whirling around and around and in between and doing all of the little acrobats they can in space in real life. Because since the Schrodinger's equation equates them to particles and waves at the same time, we depict it more like an electron cloud. However, Niels Bohr's model helps us understand their arrangement in space and helps us get the idea of how they can change between level to level. So we use them both pretty frequently, so we cover them both here in general chemistry. And with these models, with the Bohr model especially, it's easiest to see the valence shell. I have highlighted right here your outermost shell, which comes in handy when we're talking about reactivity. And we can see these valence shells, or what's the outermost orbital, based on our configurations. And when we use Bohr's model to our benefit, we can kind of take shape to how these electrons are behaving in space. So under Bohr's idea, you have s, p, d, and f orbitals that occupy a certain space. These orbitals take a general shape, where the s orbital is your lowest possible orbital and the f orbital is your highest, and you kind of increase in energy as you go up. But the shape these take is either S is spherical, the p orbital is the little dumbbell shape, d orbital is called clover, and f orbital is called double clover. All that really means is the path the electrons take as they're traveling in a bond or in a system, whether they're in phase or out of phase, either coming out to you in space or going from you in and out of phase, helps them orient themselves in a way that can best fit all the electrons in an available atom. However, there are some limitations in how they're arranged. So if you're in an s orbital, all you can occupy is one quote-unquote orbital, or one room, quote-unquote, with 2 electrons max. And if you're in a p orbital, where you can have all of this motion, you got 3 rooms, or 3 orbitals per se, that can hold 6 electrons max. In a d orbital, you have what's called this clover idea, where you have 5 rooms or 5 orbitals, and you have 10 electrons max. And in the f orbital, you have a few different options. That's the most complex system we have here. It's called a double clover with 7 orbitals, or 7 rooms with 14 electrons holding max. And as you start to build these, you can start to see how things can get spicy the further we get built out, and how things can rearrange themselves to maintain its stability. But when we're talking about these configurations are built in a predictable manner, based off of 3 main rules. The first one is Aufbau's principle, which says that the electrons are added one at a time to the lowest energy orbital first, i.e. its order of fill. Now don't go on to Google Land. Google Land will lead you astray. Here you have to learn how to use the Aufbau tree to determine the pattern of fill. So you start at the top per se, and then you just run down the tree and back around. So like, depending on your number of electrons you need to fill, you would move your way down the tree and throughout the pattern based on the arrows I have here. So if you start at the top, you first come to 1s. If you need more than one orbital, you come down to 2s, and then 2p3s, and then 3p4s, then 3d4p5s, then 4d5p6s, then eventually 4f5d6p7s, and 5f and 6d. All of those orbitals are just dependent on how much or how many electrons you have to fill. And that will make more sense as we move through it. We just have to reconcile in our head all together that the s orbital can hold 2 electrons, the p orbital can hold 6 electrons, the d orbital can hold 10 electrons, and the f orbital can hold 14 electrons. That's the principle you have to realize. But since these electrons are occupying space and they're still negatively charged things, an electron is, an electron does, it's still a negative thing, what's going to happen is you have to have some interaction rules. 2 negative things will not be in close proximity to each other for long because 2 like charges repel each other. So we have to deal with the Pauli exclusion principle, which states that in order for them to occupy the same space or in close proximity, like they have to do for bonding, they take what's called an opposite orientation or an opposite spin, which helps them occupy the similar space and maintain that stability. And when we're talking about spin, the orientation we use is arrows. Arrows help us visualize how the electrons are interacting, because if you notice, the business end of the electron is facing this way, the other business end is facing the other way, and they have all of this available space far away from each other to do their thing. So if you're talking about 1 arrowhead, that's 1 electron. If you're talking about 2 arrowheads, that's 2 electrons, and so on and so forth. And then you got like a subset to Pauli's exclusion principle. Is because they're negative, Hund's rule says they occupy the entire orbital first, then you fill the rooms. So i.e., you max out the unpaired situations. So you fill the floor before you fill the room. So I gotta fill my p floors before I fill my p orbital. So when we go through these examples, that makes more sense as we keep pushing. So what I want you to consider is how many electrons are present in chlorine. Regular degular chlorine. Chlorine has an atomic number of 17, and with the zapping skills we already know, you have 17 electrons in chlorine, because since I didn't tell you it's an ion, you assume that the positive things and the negative things, i.e. the protons and the electrons, are in perfect balance, so they're in the same number. So since I have 17 electrons to deal with, I use my Aufbau tree here, this Aufbau tree, to participate in building my electron configuration, or the address of chlorine. So we're going to use it and start it up here. So what I'm going to do is make my screen a little smaller so we can see. So I'm currently sitting here. Then I go through 1s. So we go through 1s. 1s can hold 2 electrons. That's the ugliest 1s ever. Hold on. We're going to have to fix that. S's can hold 2. S orbitals can hold 2, as we've already established. Then I keep going. I'm at, nope. I'm here. I've passed 1s. I have no more options, so essentially imagine yourself going back around the tree to the start to the next level. I then pass around 2s, so I'm 1s2, 2s2, because s is 2. So we slide back down here and go 2s2, and then we keep going down the tree until we get to 17. So 1s2, that's 2 electrons. 2s2, that's 4 electrons, and then we keep ourselves going around and down until we get to 17 electrons. Now the catch is you don't have to max out the orbital. You don't always need to put 6 electrons in P or 10 electrons in D. That's not always going to be the case, but you can never go above these limits that we've expressed right here. These limits are your limits, are hard limits that cannot be pushed. So I'm just going to knock out this configuration right here for chlorine. I got 1s2, 2s2, and then we slither over to 2p6. That gives us a total of 10 electrons. Then we're starting here at 3s2 for 12, then 3p5 for 17. And some things to take note of is in this electron configuration, I can tell a couple few different things. I can see what orbitals are occupied by the lettering. So like I can see I have a p orbital here, an s orbital there. These letters are my orbitals. And the exponents I have written here are my number of electrons in that orbital. So that's the number of electrons in the orbital. So I can already tell who's happy, who's full, how many full orbitals do I have. I can ask all kinds of questions based on how you can read these addresses or these configurations. I tend to remember the electron configurations are kind of like an address, where the orbital diagrams is a fancy word for how chlorine's house looks. So addresses and houses. It's a fun way to remember it. And the big numbers, the 1s, that prefix 1 here, these are our principal energy levels. So we can see the highest principal energy level is that 3p5, that outermost shell. So we have our principal energy levels. As I can write, that'd be great. So the principal energy levels are those big front numbers. And those principal energy levels line up with what we have here. All right? So let's get it started. Now we have the address of 1s2, 2s2, 2p6, 3s2, and 3p5. That's the address. Now, what we're going to do is determine what chlorine's house looks like. So chlorine's house follows the address, right? So I said the s orbital has one room, right? The s orbital has that one room that can hold 2 electrons max. Same with p has 3 rooms that can hold 6. What I'm talking about is these little orbital spaces that build the house. That builds the house. So to make an orbital diagram, I just take my address and start building the rooms. I got my 1s orbital. My 1s orbital can only hold 2 electrons, as I've noted in the address. So 1 electron, 2 electron. Same thing with 2s. And now here comes 2p. Now, a note for you is you do not have to always label them like I am. It just helps me understand what I've done and what I still need to do. And very clearly, if I start getting ions and more complex arrangements, I can see where I need to pull from. So I always do it. Now I'm going to follow Hund's rule and fill the floor, the P floor, before I fill a room. So I have to get all 6 of these electrons on the floor. So let's go. It's 1, fill the floor. I filled the floor. Then we got 4, 5, 6. So don't get comfortable just putting 2 in at a time, just like we do for the 1s. You have to fill the floor before you fill the room. Kind of like if you go on a trip for school or for a function, you want your own space before you got to buddy up with somebody else. So think about it like that. Then we move on to 3s. 3s has 1 room that we can put 2 electrons in. Now we got 3p. P has 3 rooms. But this p orbital only has 5 electrons in it. So we have 1, 2, 3, 4, 5. What's left over is a sad, lonely fellow that we call an unpaired electron. whereas these are paired. Anybody who has a buddy is a paired electron. Solo dolos are one unpaired electron, or however many unpaired systems you have. This is a perfect example of following Hund's rule and Pauli's exclusion principle at the same time. Because I filled the floor before I filled the room, that's how I got my unpaired electron here. And notice my arrowheads representing my electrons are following opposite spins that give them the maximum amount of space. And then I can expect my p orbital to be my highest energy level, which is my valence shell for my chlorine atom here. And I know chlorine has a -1 charge, which tells me this is liable to come off in a reaction. So it helps be predictive on how we do things. So that's how you do it. So what I want you to do is hit pause in this video and try your best to do these 5. I want you to give me the electron configuration and the orbital diagram for these 5. But let's get into it. I highly recommend you pause and try it on your own, because it's always nice if you got training wheels, but training wheels won't always be on forever. So helium, based on our periodic table, helium has 2 electrons. Helium has 2 protons, so therefore it has 2 electrons we're dealing with. So that's 1s2. That's it, that's all. And my orbital diagram would be 1s with 2 in it. Same thing with hydrogen. Hydrogen only has 1 electron because hydrogen has 1 proton, so therefore it has 1 electron, 1s1. Now aluminum has 13 protons, so therefore in contrast it must have 13 electrons to balance it out and make it neutral. So I have to account for 13 electrons. So I use my off-boff tree and I go down the columns and across and I get 1s2. Then I come to 2s2, then swing back around, I hit 2p6. Come back around, I hit 3s2. Then I get 3p1. Because if we're taking into consideration arrangements, 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, plus this extra 1 makes 13 electrons. All right, so now all we gotta do is build the house. And the house will look something like this. So I got 1s, then I got 2s, now I got 2p6, so here we go, 1, 2, 3, so now my p orbital has 3 rooms, it can hold 6 electrons, so here we go with 2p, 1, 2, 3, 4, 5, 6, now we're on to 3s, 3s only has 1 room possible, so 3s2, now here we go with 1, 2, 3 again with a 3p, but it's only got 1 electron sitting in it, so there we go. Now we're gonna swing through with scandium and vanadium. If I could grab it, that'd be helpful. Here we go. Give myself some space. All right, so now we're gonna move on to scandium. We're looking at our off-boff tree. We should have something to the effect of 1s2, 2s2, 2p6. This hands us 10 electrons. Then we got 3s2, 3p6, then we're moving into 4s2, 3d1. Same principles apply. We're going to build our address, or our house from our address. So let's get into it. We got 1s with 2 in it, then we got 2s with 2 electrons, 2p, a p orbital, has 3 rooms. They can hold 6 electrons. Notice the pattern of how I fill them. Now I'm on from 2p to 3s, can hold 2. Now 3p6, so there's a p orbital that holds 3 electrons. I have 6 electrons in it. 1, 2, 3, 4, 5, 6. Now I'm sitting with 4s. Now it has 2 in it. Now 3d, d has 5. 1, 2, 3, 4, 5. 3d, but that 3d orbital only has 1 in it. So I have 4 unoccupied orbitals in scandium. Now we're going to slide down to vanadium, if I can grab it all. We're going to slide into vanadium and do the same thing. All we're doing is following our Aufbau tree to get all the things we need. Vanadium has 23 electrons, so because it's number 23. That brings us to 1s2, 2s2, 2p6. I'm getting ahead of myself here. 3s2, 3p6, 4s2. Oh, apparently my iCloud storage is full. 4s2, and then 3d3. Because that brings us to a whopping 23. Because if we're ever in doubt, all we do is just back count. I got 2 plus 2 plus 6, that's 10 electrons. 10, 11, 12. 12 plus 6, that's 18 electrons. 18, 19. Here, I'm at 20. Then I skip down with 3 more is 23. Now I just draw my house based on my address. 1s has 2 in it. 2s is the same. There's a 2p. 1, 2, 3, 4, 5, 6. 3s. 3p. Now we're at 4s. 3d. 1, 2, 3, 4, 5. See. So now I have 3 unpaired electrons. So let me go ahead and write that in there because it's going to come in handy for you to see later. I have 1 unpaired electron. I have 1 excuse me, unpaired electron. Here I have 1 unpaired electron, but here I have 3 unpaired electrons. And that's the basis of how you do electron configurations. All you gotta do is count up your electrons you need, and you just go down Aufbau tree until you're happy and go lucky. If you have any questions, you can send me an email. I'm happy to help where I can. Until next time.